Welcome to Bedtime Astronomy. Explore the wonders of the cosmos with our soothing Bedtime Astronomy podcast. Each episode offers a gentle journey through the stars, planets, and beyond, perfect for unwinding after a long day. Let's travel through the mysteries of the universe as you drift off into a peaceful slumber under the night sky.
If you were to just go out and look up at the Whirlpool Galaxy right now, assuming you had a pretty decent telescope, of course, you'd see what looks like this beautiful spinning pinwheel suspended in the dark.
Yeah, it's really one of the most iconic images in all of astronomy.
Right. You've got the glowing central core and then those sweeping, elegant spiral arms just dotted with all that bright blue light.
It's gorgeous, and it gives you this overwhelming sense of looking at a perfect frozen snapshot.
Exactly. You see it and your brain instantly goes, okay, I understand what this is. It's a solid structure slowly spinning in space.
Like a bicycle wheel.
Like a bicycle wheel, yeah. But here is the massive secret that astrophysics have been wrestling with for, almost 2 centuries now. Based on the fundamental laws of physics, that pinwheel shouldn't exist.
It really shouldn't. It is a massive structural paradox.
It should have wound itself so incredibly tight that it destroyed its own shape billions of years ago.
Yeah.
So what we are looking at is basically a magic trick.
It is the absolute definition of a visual trick, just on a galactic scale.
Yeah.
Because like you said, you look at that sweeping shape and you intuitively assume you're seeing a solid object rotating.
Right.
Like a hurricane or a pinwheel, but you aren't. What you're actually witnessing is this highly complex dynamic engine.
And we are going to completely dismantle how that engine works today. Because unraveling why these galaxies look the way they do is, well, it's not just about admiring pretty space pictures.
No, not at all. It is fundamentally about uncovering the hidden, invisible architecture of the entire universe, including dark matter.
Right. When you look at the shape of a spiral arm, you are actually looking at the gravitational footprint of dark matter.
Yeah.
Which is just wild to think about.
It's mind-blowing.
And to really understand how wild this paradox is, we have to realize that this mystery actually predates our knowledge of what a galaxy even is.
Oh, yeah, by a long shot.
We have to go way back to 1845, to this very cold, damp field in Ireland.
Ross.
Yes. William Parsons, the 3rd Earl of Ross. This guy built what was then the absolute largest telescope in the entire world.
The Leviathan of Parsonstown, that name is just incredible.
It's so Victorian. And it was this massive, 50-foot-long tube just suspended by chains between these thick stone walls.
A total marvel of engineering for the time. And you have to remember, he was pointing this absolute behemoth into the sky at a time when we had virtually no understanding of the cosmos outside our own stellar neighborhood.
Right, so he pointed at this fuzzy patch in the sky known as M51, which is the Whirlpool Galaxy we just talked about.
Yeah.
And looking through the eyepiece of Leviathan, he becomes the very first human being to sketch a spiral structure in the heavens.
He literally drew it by hand.
He did. But here is the kicker. Nobody in 1845 thought this was a galaxy. That word, that concept, it just didn't exist in that context.
No, they called these things spiral nebulae.
Because the scientific consensus back then was so incredibly localized, right?
Exactly. The running belief was that the Milky Way was the entire universe. Full stop.
Just one big cluster of stars and that's it.
Right. So these spiral nebulae were assumed to just be swirling clouds of gas floating around right inside our own cosmic backyard.
Like maybe solar systems in the very early stages of forming.
Yeah, exactly. And it wasn't until the 1920s, during what astronomers literally call the Great Debate, that this entire paradigm just completely shattered.
Right, because you had Harlow Shapley arguing the universe was just one big Milky Way, and Heber Curtis arguing that these spirals were far too distant, that they were actually, I think he called them island universes.
Island universes, yes. And then Edwin Hubble stepped in and settled it using the Hooker telescope in California.
How did he prove it? Because it's a massive leap to go from that's a gas cloud nearby to that's a city of billions of stars really far away.
He used something called Cepheid variable stars. He found them inside these spiral nebulae. And the thing about Cepheids is that they pulse at a very predictable rate.
Okay.
And because of that predictable pulse, we can calculate exactly how far away they are. It's like a cosmic yardstick.
Oh, wow.
And Hubble proved, beyond a shadow of a doubt, that these spirals were sitting millions of light years away.
So they weren't just small clouds of gas nearby.
Not at all. They were massive, entirely independent galaxies.
Which completely rewires human understanding in an instant. We go from this cozy single galaxy universe to realizing the cosmos is populated by hundreds of thousands, if not billions, of these massive spiral structures.
It's an astronomical paradigm shift.
But, that sheer ubiquity is exactly what creates a psychological trap for us today.
Yeah.
Because you see a picture of a spiral galaxy, you see thousands of them, and they look so elegant, so intuitive.
And you just assume their mechanics must be really easy to explain.
Exactly. You fall for the pinwheel illusion.
Yeah.
So let's dismantle that illusion right now, because if a spiral galaxy were a solid disk like, say, a dinner plate spinning on your finger.
Every part of that plate completes a rotation in the exact same amount of time.
Right. The inner part near your finger and the outer rim are moving in total lockstep. But galaxies are not solid plates.
No, they are incredibly fluid agglomerations. It's just stars, gas, dust, and a whole lot of dark matter.
Which means they have to obey orbital mechanics, just like anything else. The stars in a galaxy are orbiting a central mass, much like the planets in our solar system orbit the sun.
Exactly. And Johannes Kepler taught us centuries ago that in a system like that, objects closer to the center of gravity orbit much faster than objects on the outer edge.
Right. So Mercury zips around the sun in, 88 days? But Neptune takes something like 165 years.
That's differential rotation in a nutshell.
Okay, so if you apply that differential rotation to a galaxy, you hit an immediate brick wall logically.
Yes, of what?
Because if the stars in the inner disk are whipping around the galactic core at incredible speeds, while the stars out on the outer rim are barely crawling along.
Right, they're taking hundreds of millions of years to make one lap.
Then, just by basic orbital mechanics, shouldn't those distinct spiral arms just stretch out, wrap around the core, and basically spool up like spaghetti around a spinning fork?
You've just perfectly articulated what astrophysicists call the winding dilemma.
The winding dilemma.
Yeah, it is the fundamental problem of spiral galaxies. Because of that differential rotation, those sweeping arms should act exactly like a string wrapping around a spinning top.
But they don't.
No, they don't. And they shouldn't survive very long if that were the case. In galactic terms, a single rotation might take a couple of 100 million years, right?
Yeah.
After just a few rotations, those distinct arms should be wound so tightly that the spiral pattern is completely erased.
It would just look like a blurry circle.
Exactly. The galaxy should just smear out into a smooth, featureless, glowing disk.
But wait, our own Milky Way is roughly, 13.6 billion years old?
Something like that, yes.
And the galaxies we see out there have been spinning for billions of years too. So if the winding dilemma is correct, all spiral arms should have vanished eons ago.
We shouldn't be seeing any of them today. None.
Which means the simple rotation explanation completely fails.
Completely. And that glaring contradiction just sat there, honestly mocking astronomers, until the 1960s.
When C.C. Lin and Frank Hsu stepped in?
Right. They proposed what is now the prevailing framework for solving this whole mess, which is called density wave theory.
I love diving into density wave theory because it's one of those concepts that sounds super intimidating, but the best way to visualize it is something everyone listening to this has unfortunately experienced firsthand.
A traffic jam.
It is, at its core, a cosmic traffic jam.
It really is the single most accurate analogy we have for this.
Okay, so think about a massive multi-lane highway, and there's an area where maybe there's a stalled car on the shoulder, or two lanes merge, causing a bottleneck.
So a localized traffic jam forms right there.
Right. Now imagine you are in a news helicopter hovering way above the highway, looking straight down. From your perspective up there, that dense cluster of slow-moving cars, the traffic jam itself, stays in the exact same spot on the highway for hours.
It barely moves forward at all.
It just sits there. But the individual cars making up that jam are constantly changing.
Exactly.
The car zips down the open highway at 70 miles an hour. It hits the back of the traffic jam, the driver slams on the brakes, and the car crawls forward, tightly packed with all the other cars.
Just inching along.
Right. But eventually it clears the bottleneck, hits the open road again, accelerates, and leaves the jam behind. The cars were always flowing through, but the traffic jam remains in place.
And Lin and Hsu proposed that this is exactly what is happening in a spiral galaxy.
So the arms aren't physical things?
No. The spiral arms are not fixed structures made of the same stars forever. The arms are the traffic jams.
So an arm is just a region of space where things are moving slower.
It is a visible region of higher density, a density wave sweeping slowly through the galactic disk. And it moves much, much slower than the actual stars and gas.
Okay, so as a star orbits the center of the galaxy, moving at its faster differential speed, it eventually catches up to this slower moving density wave from behind.
Yes. And when the star, and more importantly, the massive clouds of interstellar gas enter this wave, the local gravitational pull is suddenly much stronger because everything is bunched up.
The gas hits the brakes.
It hits the brakes hard. The gas clouds compress violently as they bunch up in this traffic jam. And in astrophysics, when you take a massive cloud of hydrogen gas and you compress it like that, you trigger what's called the Jeans instability.
The Jeans instability, what does that do?
The gas begins to collapse under its own gravity, which creates these massive shock waves.
Which is exactly what triggers star formation.
Yeah.
You are basically squeezing the cosmic clay until it ignites.
Precisely. This localized compression inside the traffic jam sparks furious stellar nurseries. You get the birth of these massive, incredibly hot, short-lived stars.
The O and B type stars, right?
The O and B stars. And these stars burn with a fierce, brilliant blue light, and they ionize the surrounding gas.
Which creates those glowing red HII regions we see in the telescope images.
Exactly. This fierce illumination is what suddenly makes the density wave visible to us. The arm lights up entirely because of the newborn stars.
That is so cool. And then what happens is the wave just keeps slowly moving on.
Well, those massive blue stars, they live fast and die young. They often explode as supernovae before they even manage to exit the traffic jam.
Wow, they don't even make it out.
They don't. But the smaller, longer-lived stars, like our sun, eventually pass all the way through the density wave. They exit the front of the traffic jam, speed back up, and drift out into the darker, quieter regions between the spiral arms.
Just waiting to lap the next wave.
Exactly.
It is an incredible reframing of reality. We're looking at a process, not an object.
That's the perfect way to phrase it.
But density wave theory has a major vulnerability, doesn't it?
It does, unfortunately.
Because it explains why the arms don't wind themselves into oblivion, but it introduces a whole new problem regarding how long they can survive at all.
Right. It's the problem of dissipation. Because these density waves aren't magically exempt from the laws of thermodynamics and fluid dynamics.
They still have to obey the rule.
Exactly. Over immense stretches of time, physical forces within the galactic disk, like the friction of all those gas clouds colliding, and complex gravitational resonances known as Lindblad resonances.
Lindblad resonances.
Yeah, they're basically gravitational friction points. And all of this should eventually damp down these waves. The energy of the traffic jam should dissipate.
Just smoothing out the density wave until the spiral arms fade away entirely.
The traffic jam should eventually just clear.
But everywhere we look in the universe, spiral galaxies are just staring back at us. They are incredibly common.
Which means the ultimate mystery remains. What sustains these waves over billions of years? What keeps the traffic jam from clearing out?
Right. And to answer a question about longevity, about how something sustains itself over billions of years, you can't just look at the universe as it exists today. You have to look at its history.
You have to trace the evolutionary timeline of these structures.
And that brings us to an absolute marvel of modern engineering, which is the Euclid Space Telescope.
Euclid is a phenomenal observatory. It was launched by the European Space Agency recently, and it's positioned out at Lagrange Point 2.
Which is a stable orbit about 1 million miles from Earth.
Right. And its observational capabilities are just staggering. It was specifically designed to look at the wide field geometry of the dark universe.
And the scale we are talking about here involves measuring the redshift of galaxies all the way out to a value of z equals 2.
Yes.
Now, let's make sure everyone has a really firm grasp on what that actually means, because it's vital to this whole investigation. We hear the word redshift thrown around a lot in space news. What is physically happening to the light that allows us to use it as a cosmic clock?
It all comes down to the expansion of the universe. Space itself is stretching. So as light from a distant galaxy travels across the universe toward our telescopes, the very fabric of space it is traveling through is expanding. And this expansion literally stretches the wavelength of the light itself.
Like stretching a coiled telephone cord.
Exactly like that. And in the electromagnetic spectrum, longer wavelengths correspond to the red end of the spectrum.
Ah, so it shifts red.
Right. So the longer light has been traveling through expanding space, the more its wavelength is stretched, and the redder it appears to us.
That makes total sense.
Right.
So by measuring exactly how much the light from a galaxy has been shifted toward the red, we can calculate exactly how long that light has been traveling.
Exactly. So when astronomers say Euclid is looking at galaxies at z equals 2, that specific redshift value translates to a travel time of roughly 10 billion years.
10 billion years. That The scale is hard to wrap your head around. The light hitting Euclid's sensors left those galaxies 10 billion years ago.
We are literally watching a movie of the universe as it existed 10 billion years in the past.
Which is profound, especially when you consider the universe itself is estimated to be around 13.8 billion years old.
Right. So we're looking back at a relatively young cosmos, a time when galaxies were still in their really formative, wildly active stages.
Now, I have to assume Euclid wasn't built for $1 billion just to count spiral arms, right?
No, definitely not.
What is its primary mission, and how did it get hijacked for this specific structural mystery?
So Euclid's primary mandate is to define the link between dark energy and the universe's expansion rate. It does this by measuring redshift to see how fast galaxies are moving apart, and by measuring the precise shapes of billions of galaxies to study weak gravitational lensing.
Weak lensing being the way the gravity of invisible dark matter bends and distorts the light of galaxies sitting behind it.
Exactly. By meticulously mapping these tiny, tiny distortions in shape, Euclid is creating a 3D map of the universe's dark matter scaffolding.
Okay, so where do the spiral arms come in?
Well, here is the brilliant secondary use of all this data. To measure those tiny distortions caused by lensing, Euclid has to take incredibly sharp, high-resolution images of galaxies across vast distances.
Oh, I see. And a high-resolution image meant to study tiny distortions is also a perfectly clear picture of a 10-billion-year-old spiral arm.
Precisely. It allows astrophysicists to perfectly distinguish the spiral arms, the bulges, and the disks of galaxies sitting billions of light years away.
It effectively lets us see exactly what spiral galaxies looked like in the ancient universe.
Right. And then we can compare the structural dynamics of 10 billion years ago to the galaxies sitting in our local neighborhood today.
Which brings us to the massive scale of the research we are unpacking today. Because this wasn't just a survey where astronomers picked, a dozen of their favorite photogenic galaxies.
No.
A team led by Beverly Smith, who is a professor of physics and astronomy at East Tennessee State University, utilized this Euclid data to examine the structures of over 380,000 galaxies.
380,000. It is just difficult to overstate how revolutionary that number is for observational astronomy.
Because historically, studies on galactic morphology might look at a few hundred, right?
Yeah.
Maybe a couple of thousand galaxies if they were ambitious.
Exactly. But when you're trying to solve a puzzle about the mechanics of an entire class of celestial objects, scale is everything.
Right. If you only look at 100 galaxies, you are totally blind to the macro trends. You might just be looking at a cluster of weird anomalies.
It's like trying to understand global human behavior by interviewing 10 people at a single coffee shop.
You need the census data.
Yeah.
And when you study 380,000 galaxies across 10 billion years of cosmic time, you can finally separate the rule from the exception. You get undeniable statistical certainty.
Absolutely. But of course, analyzing 380,000 highly detailed images presents an immediate, massive logistical problem.
Yeah, I'd imagine.
You cannot have graduate students sitting in a dark room manually counting the spiral arms on nearly 500,000 images.
It would take lifetimes.
You really would.
So how do they do it? You mentioned they used a tool called Euclid Zubot. What exactly is that?
So Euclid Zubot is this highly sophisticated machine learning algorithm. It's an artificial intelligence specifically trained to recognize and categorize galactic structures.
Okay.
But what's fascinating is how it actually learned to do this, because it was trained on the backs of citizen science.
Like the Galaxy Zoo project.
Exactly like Galaxy Zoo. For years, that project allowed hundreds of thousands of everyday people to just log online, look at telescope images, and answer really simple questions.
Things like, is it a spiral? How many arms does it have? Is the center round or cigar-shaped?
Exactly. And it turns out everyday people are remarkably good at pattern recognition, often much better than early computer models.
So by feeding millions of these human-classified images into the machine learning model, Zubot learned the subtle visual cues of galactic morphology.
Right. So when the Euclid data came down, the researchers deployed Zubot to parse this staggering data set, basically standardizing the classification of 380,000 ancient galaxies in record time.
And to classify them, they had to force all this visual chaos into a structured taxonomy. They focused heavily on the anatomy of the spiral, specifically. How many arms does this thing actually have?
Yeah.
And they divided them into three main macro categories.
The first category is the grand design spiral galaxy. These are the absolute showstoppers.
The classic look.
Right. They have two long, continuous, highly defined, symmetrical arms extending outward from the galactic center. M51, the Whirlpool Galaxy, is the quintessential example of this.
When you close your eyes and picture a galaxy, you are picturing a grand design.
Exactly.
Okay, so grand design is the classic two-armed structure. Now, if I'm placing bets on what happens when a galaxy fails to form those perfect two arms, I'd assume things just get wildly chaotic.
Because space is a violent place.
Exactly. Space is violent and messy. Galaxies are colliding. Gas clouds are fragmenting. I'd expect a ton of messy, multi-armed structures to be out there.
That leads directly to the second category, which is the multi-armed galaxies. And exactly as it sounds, these are systems that possess 3 or more relatively long arms.
Yeah.
They are visually busier, they're more complex, and they completely lack that perfect bilateral symmetry of the grand design.
And what happens when a galaxy can't even hold long arms together at all? Like it just completely falls apart structurally.
Then you arrive at the third category, which is known as flocculent galaxies.
Flocculent. It sounds like an insult you'd yell at someone in traffic.
It really does. But it actually means having a loosely clumped or fluffy texture, like tufts of wool.
Oh.
In galactic morphology, flocculent spirals don't have sweeping, continuous highways of stars. Instead, their disks are filled with many short, fragmented, totally disconnected arm pieces.
Like little fluffy patches.
Yeah, they look like glowing, patchy clouds scattered in a very loose spiral pattern. It's highly localized instability rather than a galaxy-wide density wave.
All right, so we have our taxonomy. Grand design, which is 2 arms, multi-armed, which is 3 or more, and flocculent, which is fragmented fluff.
Right.
The researchers run the Euclid ZooBot on the 380,000 galaxies. But first off, they have to deal with the messy reality of data collection, right? Because nothing is ever perfectly clean in astronomy.
Oh, absolutely. They had to discard roughly 20% of the sample right out of the gate.
Wow, 20%.
Yeah, in astronomy, you are always fighting observational hurdles. Even with a telescope as incredibly powerful as Euclid, some galaxies are just too faint, or they're oriented edge-on so you can't even see the disk to count the arms.
Or obscured by foreground dust, I imagine.
Exactly. Furthermore, they really had to account for something called Malmquist bias.
Okay, break down Malmquist bias for us, because that sounds important.
It's an inherent selection effect in observational astronomy. Basically, the further away you look, the harder it is to see dim objects.
Right, obviously.
So, at extreme distances, your data set becomes heavily biased toward only the brightest, most luminous galaxies because the fainter ones simply don't register on the sensors anymore.
So you think there are only bright galaxies out there, but really you're just missing all the dim ones.
Exactly. The researchers had to rigorously filter the ZooBot results to ensure they weren't just categorizing noise or falling prey to this bias.
But once they cleaned the data and focused on the vast majority that remained clearly classifiable, the statistics that fell out of this 10 billion year survey are just staggering.
They really are.
They found that an overwhelming 60% to 70% of the spiral galaxies are 2-armed grand design spirals.
It is the overwhelmingly dominant standard model of the spiral universe by a massive, massive margin.
Which means my assumption about a chaotic, messy universe being the norm is just completely wrong. Order dominates.
It does. Order dominates. Following that, about 15% to 20% fall into the 3-armed, multi-armed category.
Which leaves a pretty tiny statistical sliver left over.
And this is where the data threw a really fascinating curveball. Only about 1% of the spirals in the entire enormous sample are classified as 1-armed galaxies.
Wait, a 1-armed galaxy? Logistically, how does that even balance?
It doesn't, really.
We just spent all this time talking about density wave theory, Keplerian dynamics, and the symmetry of gravitational fields. A single arm extending out from the core seems like a massive contradiction. It should be entirely lopsided.
It is completely lopsided, which highlights just how rare and structurally tenuous they really are.
So what's going on with them?
What the Euclid data shows, when you correlate the arm count with the physical properties of the galaxies, is that these 1-armed anomalies have uniquely low masses compared to their 2-armed cousins.
They are the lightweights of the galactic world.
Exactly. And mass dictates gravitational stability. When a galaxy is a lightweight, its gravitational anchor is extremely weak. Its center of balance is highly susceptible to disruption.
Like a small boat in a storm.
Right. These 1-armed or lopsided spirals, they're sometimes called Magellanic spirals, they are almost always the result of a trauma.
A trauma? Like what kind of trauma?
A gravitational interaction with a neighboring dwarf galaxy. Or maybe an asymmetrical infall of cold gas from the intergalactic medium. Or even a localized lopsidedness in their surrounding dark matter halo.
Wow.
Because they don't have the internal mass to stabilize themselves, a disturbance can trigger a massive density wave on one side of the galaxy without having the sheer gravitational force required to form a symmetrical balancing wave on the opposite side.
So it's literally a localized injury in a less anchored system.
Perfectly said.
That makes perfect sense. The heavier the ship, the harder it is to capsize. Which brings us perfectly to the core mechanics of shape, because finding out that 60 to 70% of galaxies are two-armed isn't just a fun piece of trivia.
No, it is a massive clue.
The number of arms a galaxy has is directly, fundamentally tied to its internal anatomy.
This is where we transition from observing the what to finally understanding the why of the two-armed dominance. The Beverly Smith study didn't just count arms, it cross-referenced those counts with the structures of the galactic cores. And they found a rock-solid connection between the number of spiral arms and the mass of the galaxy's central bulge.
Now, the central bulge being that incredibly dense, roughly spherical concentration of older stars at the very heart of the galaxy. It's the yolk of the fried egg, right?
Yes. Our own Milky Way has a significant central bulge, anchored by a supermassive black hole and millions of densely packed ancient stars.
And what did the Euclid data reveal about these bulges?
It unequivocally reveals that galaxies possessing large, massive central bulges almost universally express two dominant spiral arms.
Why? What is the physical mechanism that forces a massive bulge to equal exactly two arms?
It is deeply rooted in the fluid dynamics and the gravitational rotation curves of the galaxy. Remember Vera Rubin's pioneering work on rotation curves?
Right, where we found that in many galaxies, thanks to dark matter halos, the outer stars orbit much faster than Keplerian physics alone would predict.
Exactly. But when a galaxy has a massively dense, heavy central bulge, the sheer concentration of baryonic mass at the core dominates the inner gravitational field.
The gravity at the center is overwhelming.
Absolutely overwhelming. This massive central concentration leads to what astrophysicists call a declining rotation curve in the inner regions of the disk.
Okay, break that down. What does a declining rotation curve mean for the actual stars in the disk?
It means the stars in the inner lanes, which are held in the crushing grip of that massive bulge, are being whipped around at phenomenally high speeds.
Right.
But as you move outward from the bulge, that orbital velocity drops off severely before eventually leveling out. There is a massive, sharp difference in velocity between the inner disk and the outer regions.
So the inner lanes of the track are moving at 200 miles an hour, and the outer lanes are moving at 20 miles an hour.
Yes. And that extreme velocity differential creates an intense physical force called a large shear rate.
Now, earlier we talked about a traffic jam, but how does shear rate apply here? Because if I slide a book across a table, there's shear, but a galaxy is a spinning fluid.
Right. Rotational shear in a fluid is entirely different from linear shear.
Okay, give me an example.
Imagine a cup of black coffee, and you pour a thin ribbon of cream into it from the center out to the edge.
Okay, got it.
If you stir the center incredibly fast, but the outer edge barely moves, the liquid in the center is constantly lapping the liquid on the outside. The friction and the differential speeds stretch and tear that ribbon of cream.
Wow.
In a galaxy, this powerful rotational shear acts upon the interstellar gas and dust in the exact same way.
And how does that destructive tearing force lead to an elegant, two-armed grand design? Seems like it would just make a mess.
By mercilessly destroying anything smaller.
Oh.
If a localized, flocculent little arm tries to form in a galaxy with an intense shear rate, the extreme velocity differential stretches it and shreds it before it can ever establish itself.
It just rips it apart.
Exactly. The math of spiral density waves, specifically those Lindblad resonances we mentioned earlier, dictates that in a high shear environment, the only density wave mathematically stable enough to survive being ripped apart is a massive, symmetrical, two-armed wave.
So the shear literally irons out the wrinkles.
It really does. It forces the chaotic gas into two sweeping, dominant highways because they are the only structures robust enough to withstand the extreme physics of the disk.
That is breathtaking. The heavy central bulge is basically acting as a brutal gravitational metronome, dictating the structural rhythm of the entire galaxy.
And the inverse is equally true. When you look at galaxies with smaller bulges, less massive centers, They lack that severe declining rotation curve.
So they do not have that intense rotational shear.
Exactly.
If you don't have that massive anchor, if your center is lightweight, you don't have the sheer force to iron out the wrinkles.
Sure.
The galaxy would just fragment into a bunch of smaller, messy arms.
You've just logically deduced the existence of the multi-armed and flocculent galaxies. Without the dominant shear of a massive bulge, localized instabilities are allowed to thrive. You get 3, 4, or dozens of fragmented arms because nothing is strong enough to rip them apart and force them into a grand design.
So the structure of the entire galaxy is literally a physical symptom of the mass at its dead center.
It is entirely dictated by it.
And what makes this so incredibly satisfying is that this massive observational data set from Euclid finally provides the hard proof for our theoretical models.
Yes. For decades, astrophysicists have been running n-body computer simulations in supercomputers, basically modeling the behavior of millions of virtual stars.
Right.
And in those simulations, if you artificially inject a massive central bulge, the simulation invariably produces a 2-armed spiral.
But a simulation is just math until the universe actually confirms it.
Exactly. And Euclid's observation of 380,000 galaxies across 10 billion years definitively confirms the theory. It's beautiful.
But the internal mass isn't the only thing the researchers tracked, is it? They also looked at the star formation rates, or SFRs, basically correlating the structural anatomy with how aggressively the galaxy is churning out new stars.
This adds a critical temporal layer to our understanding. It shows us the life cycle and the temperament of these systems.
And the correlation they found is remarkably stark. The study reveals that 2-armed spirals, on average, have significantly lower star formation rates.
Which might seem counterintuitive at first.
Right. Now, we should note that within the parameters of this specific study, the researchers attribute this lower rate to the fact that the 2-armed galaxies in their sample tended to have lower overall disk gas masses available for star formation, despite having those heavy central bulges.
Right. The fuel tank was running a bit low.
Exactly. But the contrast is what really matters here. Contrast that low rate with the 3-armed spirals, which boast much higher star formation rates.
The structural chaos of the 3-armed systems is directly mirrored by their frantic stellar production.
The best way to visualize the difference between these galaxies is to think about urban development. A 3-armed galaxy, with its high star formation rate and lack of a stabilizing shear, is like a booming, chaotic, new frontier town.
I love this analogy.
There is raw material everywhere. Construction cranes dominate the skyline. New neighborhoods are being rapidly built and then torn down. It is incredibly active. It's churning with energy, but structurally, it's a bit of a mess. There's no master plan.
It's a highly volatile environment.
Exactly. But a 2-armed grand design galaxy is like an older, highly structured, settled metropolis. Think of a city anchored by a massive, historic, densely packed downtown. That's your central bulge.
Right.
Because of that anchor, the major highways and transit lines, the 2 spiral arms, are rigidly established. There isn't wild, uncontrolled new construction happening in every single corner. The available resources are managed, things have quieted down, and the city has fallen into a stable, enduring, long-term rhythm.
That analogy perfectly captures the internal dynamics. The multi-armed systems are active, chaotic, and just churning through their gas reserves, while the 2-armed systems are settled, heavily anchored, and far more stable in their stellar production.
It's a totally different stage of life.
It really is. But if we pull back even further, away from just the visible stars and the gas, we arrive at the most profound implication of this entire 380,000 galaxy survey.
This is where we must reckon with the invisible scaffolding of the universe.
We have to talk about dark matter.
So,
a galaxy's arms, its rotation curve, its sheer rate, all of these mechanics we've been discussing are entirely dictated by gravity. But in our universe, the visible matter, the stars, the dust, the glowing gas, makes up only a tiny fraction of the galaxy's total mass.
the vast majority of the matter exerting all that gravitational force is totally invisible.
Right. Dark matter doesn't interact with electromagnetism at all. It doesn't emit light. It doesn't reflect light or block light. You could literally have a clump of dark matter right in front of your face and you would never see it.
But it exerts a massive gravitational pull. It is the invisible skeleton holding the glowing meat of the galaxy together.
What a visual. Yes. And because the sheer rate that shapes the arms is entirely dependent on the total gravitational potential of the galaxy, the spiral arms are effectively tracing the gravitational pull of everything in the galaxy, both seen and unseen.
Now, you might be thinking, if dark matter is completely invisible, how can looking at a photograph of glowing stars tell us anything about it?
Because the glowing stars are forced to obey the gravity of the dark matter. Beverly Smith and her research team point out a really revolutionary concept here. Analyzing the arm structure of these galaxies gives astronomers a brand new proxy to estimate the concentration and distribution of dark matter deep within galactic centers.
The arms are not just pretty features catching the light. They are the visible footprints of invisible mass.
Exactly. By reading the number of arms and measuring the tightness of their winding, we can map the dark mass that we cannot observe directly.
It's like looking at the ripples on the surface of a pitch-black pond. You can't see what's beneath the water, but by studying the size, speed, and shape of the ripples on the surface, you can determine the exact mass of the boulder that was thrown in. You don't need to actually see the boulder to know how heavy it is.
That is exactly what this Euclid data provides. A catalog of 380,000 ripples, allowing us to map the invisible boulders of the ancient universe.
That is just incredible.
But, as with all grand theories in astrophysics, we have to acknowledge the messy, uncompromising reality of nature.
Because the universe refuses to fit perfectly into our neat, human-made taxonomies.
Never.
Right. As satisfying as the grand design, multi-armed, and flocculent categories are, a galaxy is a fluid dynamic system spanning 100,000 light-years. It's never truly that simple, is it?
Not at all. And the researchers are admirably transparent about this caveat. They explicitly note that very few galaxies in the universe are completely two-armed or completely three-armed in a mathematically perfect sense.
There's always some structural noise.
Always. There is a continuous spectrum of morphologies. When you look closely at these high-resolution images from Euclid, even in a beautiful grand design spiral, you see imperfections.
What kind of imperfection?
You see branches splintering off the main arms. You see what they call feathers, which are these tiny spurs of gas and newborn stars bridging the dark gaps between the major lanes.
So it's a living system, not a perfect geometric drawing.
Exactly. In fact, within the field of galactic morphology, there is an entirely different classification system developed by Bruce and Deborah Elmgreen that involves 12 distinct categories.
12 categories?
Yeah, it was designed specifically to account for all these subtle variations. The branching, the spurs, the varying degrees of flocculence.
So wait, why didn't the researchers use that highly detailed 12-category system for this Euclid study? Why stick to the simpler 3-category macro approach?
It basically comes down to computational and practical limits.
Oh, because of the AI.
Right. Implementing a highly nuanced 12-category system on 380,000 separate galaxies using current machine learning software on a dataset this vast is simply too difficult right now.
Because the subtle differences between, say, Category 7 and Category 8 in a 12-tier system are incredibly hard for an AI to parse consistently.
Exactly, especially across fuzzy 10-billion-year-old images. Even with the mitigation of observational biases, using the 3 broader categories allows astronomers to confidently spot the macro trends first.
It establishes the baseline.
Right, the baseline upon which deeper, more granular AI analysis will eventually be built.
Which brings us back to the ultimate mystery we started with, the longevity of the traffic jam. If density wave theory explains how the arms don't wind up, but struggles to explain why physical forces don't eventually damp the wave out of existence, what is the grand synthesis of this new data? How do these arms survive?
The massive scale of the data provides compelling, perhaps definitive hints. Because the 2-armed grand design spirals utterly dominate the sample across 10 billion years of time, it strongly suggests that massive, settled disks, the ones with heavy bulges and dense dark matter halos, are highly likely to maintain stable, long-lived 2-arm patterns.
The heavy center anchors the wave indefinitely.
Yes. The sheer central mass and the resulting relentless shear forces act as a perpetual stabilizing mechanism. It constantly re-energizes the density wave, fighting against the dissipation, keeping the traffic jam locked in place for billions of years.
Well, what about the multi-armed ones?
Well, the multi-armed and flocculent galaxies are much fewer in number and are associated with lower central masses and high chaotic star formation.
So what does that imply for their longevity? If they don't have the massive anchor, what happens to their density waves?
It strongly suggests their structures are entirely transient or recurrent.
Meaning they don't last.
Right. A 3-armed or flocculent shape is likely not a permanent state of being for a galaxy. It might just be a temporary phase it goes through, perhaps lasting a few 100 million years before the dynamics scramble the arms entirely, or before the galaxy accumulates enough central mass to finally settle down.
They're continuously tearing themselves apart and reforming.
Yes, it's a temporary burst of chaos versus a permanent structural equilibrium. But the researchers also introduced a truly fascinating sub-theory about the two-armed galaxies themselves, didn't they?
They did. They suggest that we might actually be looking at two completely different physical phenomena that just happen to produce the exact same visual shape.
Which is wild to think about.
They posit there might be two distinct subtypes of two-armed spirals. Meaning what? Are some of them fake two arms?
Not fake, but driven by entirely different mechanics. Some two-armed spirals might be transient.
Like how?
For example, if a galaxy without a massive bulge has a close gravitational encounter with another passing galaxy, tidal forces can temporarily whip its disk into a two-armed shape.
Oh, just from the gravitational pull of the neighbor.
Right, but without the internal mass to anchor it, that shape will eventually fade as the wave dissipates.
But the other subtype?
The other subtype, the ones possessing the massive central bulges and the dense dark matter cores, are permanent fixtures. They are structurally locked into that grand design shape for eternity by their own overwhelming internal gravity.
That is deeply profound. We started this conversation by looking at a picture of a spiral galaxy as a static, simple object, a frozen pinwheel in the night sky.
And we end up here.
Right. Through the lens of Lord Rosse, Edwin Hubble, and now the Euclid telescope looking back 10 billion years, we have come to understand them as incredibly dynamic, deeply complex fluid engines.
They are driven by massive central bulges, fierce rotational shear, the frantic, explosive churning of stellar nurseries, and the inescapable invisible hand of dark matter halos.
And while we haven't completely mapped out every nuance of how every single density wave sustains itself, we have crossed a massive threshold.
We really have. We are no longer just cataloging pretty shapes.
We are literally reading the anatomical structure of a galaxy to decode the parts of the universe we cannot observe directly. We are reading the shadows.
That's a beautiful way to put it.
Which leaves us with one final, very provocative thought to mull over. If multi-armed chaotic galaxies are these highly active transient systems burning through gas and churning out new stars, and if massive settled bulges dictate stable, lower activity, two-armed patterns, does that mean a two-armed grand design spiral is the ultimate retirement state of a galaxy?
It is a stunning extrapolation. As the universe continues to expand and age, and as all that dark matter and intergalactic gas finally settles down, condenses, and merges into central bulges over eons.
Will all the wild, multi-armed, flocculent galaxies eventually run out of chaotic energy?
Will they all eventually evolve into grand, stable, slowly rotating two-armed structures drifting quietly in the darkening cosmos?
It is an incredible thing to think about. When you step outside tonight and you look up into the dark sky, remember that the shapes you imagine out there are not just swirling stars caught in the frozen snapshot. They are a massive, billion-year-old cosmic traffic jams, anchored by supermassive black holes, locked in an invisible web of dark matter, slowly aging in the deep.